Hello all. In this video, we're going to take a look at image generating machine learning models. They are an interesting, different architecture. In understanding the big picture is not so hard. I'll show you some of the technical details as well, but we're not going to get into really fine-grained details at all. But I will, as I have promised in the previous video, I will include some links in the description for the video. These links are also in the materials that I'm posting for my students that you can take a look at if you want to learn more. In the process, we're going to take a little bit of a side detour to talk about encoder-decoder models as a pattern. And should be of interest to you, even if you're more interested in text generating AI models. They are also built often as encoder-decoder models. So you'll get a little bit of a sense of how they might work. And then we will focus mostly on the formats that show up in the context of generating images. So let's start by just thinking broadly about generative AI. The first thing to know about generative AI is that there are multiple architectures that are in use. There are the transformer architectures that have been mostly applied to text and to some extent to images as well. But not as much with image generation, often for other image processing computer vision tasks. There are also diffusion models, which are somewhat different from the others, and generative adversarial networks were the predecessor to the diffusion models. And then there are other models that show up in this general area. So ChatGPT, the name refers to generative pre-trained transformer. That was initially a text-based system completely. It used a transformer model underneath. These days, the big push is in focusing on multimodal systems. So they've been revising the architecture, adding on to it. I'm not actually sure of all the details of how the current ChatGPT works, but it does now integrate image generation and image understanding, computer vision sorts of tasks in what it does. And there has always been an interest with image generation in connecting image generation to text. We want people to be able to say what it is they would like the AI system to generate, and that is what's usually done in text. So in text generators, you usually see this transformer architecture. It's an encoder-decoder model. And usually with image generation, you'd see something like the GANs, the generative adversarial networks, or the diffusion models. The diffusion models are much more common, but you do occasionally run across GANs, and you find data sets of GAN-generated images as well. We're going to take a little side trip to talk about encoder-decoder models as a pattern because they are important in many places in machine learning. So encoder-decoder models, I have a picture here. I don't think I can get it quite all in view at one time. Encoder-decoder models have two parts. They have an encoder phase and a decoder phase. And so you can see here I have this illustration of what this kind of model looks like. Input comes in and it goes through the encoder phase, which you could think of for images as being something like the CNN feature detection, which gradually, as we remember, it shrinks the size of the data, it condenses, it looks for patterns upon patterns, and you end up with a compressed representation of the image that may be significantly smaller than the original image was. The decoder then is trained to unpack that representation and produce some kind of output. So it's taking that condensed representation that we've generated and it unpacks it back out into something that might be large. This could be used for image segmentation. It can also be used for generating the original image again, which might seem like a strange task. Why train a model to take in an image, do some things to it, and then produce that same image as output? And the reason that we care about that, the reason that that's an interesting task, is the way that I've drawn this. There's this shrinking down. In the middle, if we have a successful model that can generate the same image on the output as the input image was. And at some point in the middle, it's been squeezed through a bottleneck. At that moment, it had a compressed representation of the image. Now, so you could, once you train a model to do this task, you can chop it in half, split apart the encoder and the decoder, and then, for instance, have an image compression algorithm that might be specific to a certain kind of data, whatever you trained the model on. But it can take the original data and squish it down into a compressed representation. You can move that around, and then at some point you can uncompress it again and get the original image back. So it creates a vectorized representation of the data. Sorry, I'll jump to the wrong point in my notes. So it turns that data into just a smaller box of numbers somehow. Then the thing that people did early on when they were first trying to do image generation is they trained this kind of model to do this auto-associative task. Same output is expected as the input that came in. We just want it to repeat it. So that they could then chop the two in half, take the decoder part of the model, and feed random noise into it and see if it could then generate images. And what happened was, yes, the answer is yes, it could. Not great images, but it was a starting point. And this general idea of an encoder phase followed by a decoder phase has just turned out to be very popular, very powerful across quite a number of different applications, everything from ChatGPT to image generation systems, even if they're doing something more complicated than the simple encoder-decoder I've been describing here. Okay, so I want to take a look at one specific computer vision related encoder-decoder. I don't know why particularly, but this has always been one of my favorite architectures. I think it's just because it's such an elegant shape. This is called the UNet, and you will see it crop up in a number of other places. It's a U-shaped network. You have an input image that comes in on the left, and you can see that these are just convolutional layers. So it does a couple of rounds of convolution. In fact, if you look at this first pattern that's leading us from the start down to the midpoint, first of all, this is the encoder phase, and it's a lot like VGG. The original UNet was built to be a lot based on the VGG model. So we have convolutions and then pooling, and then convolutions and then pooling, repeated several times. And when you get down here, this is that bottleneck part. We have only 1,024 layers, each of them quite small, and that is our compressed representation of our input image. In the second half of the UNet, what you see is we've added another kind of layer called an upsampling layer. I think it's been mentioned here or there, which basically scales up an image. So it takes the image and it's just increases its size. So you see it's scaled up and then it's run through more convolutional layers and scaled up and run through more convolutional layers, all the way until you produce the output. This particular image was based on an image segmentation task that used this particular architecture to segment images. So it's been successful. The one piece that I want to talk about that I haven't mentioned yet is the yellow layers that are marked here. And you see they have blue arrows that cross across. So what makes this, if you didn't have these blue arrows, this wouldn't actually be U-shaped. It could just be flat, encoder and then decoder. But in fact, we have these arrows here and they make a really big difference. So what's happening is just before we do pooling on this output of this second round of convolution, we save that layer and we pass it across and concatenate it with what's coming up out of the decoder thus far. So the information that we had at that moment in time is preserved and reused in the decoder phase. So the decoder has access to periodic information from the encoder at different stages of its compression and decreasing of the original information. So this is the UNet. It's definitely an encoder-decoder. It has all this structure of like compressing something down and then unpacking it back out. It can be used for auto association. It can be used for image segmentation. I have seen people attempt to use this to do image generation. They would train it and then they would break it apart right here and they would try making a vector or an array, a matrix with random values in it and just see what the decoder would produce. And as I said, it's not great, but it was a start when people were first trying to figure out how to use deep learning to generate images. Okay, let's talk about GANs. So GANs were the first widely successful image generation system, and they were quite popular for some time. If you look for deepfake data sets right now, many of them are still GAN-based, even though GANs have been somewhat superseded by the diffusion models that have been much more successful in producing realistic images. So GAN stands for Generative Adversarial Network. The GAN is a really, really interesting architecture. I like this architecture. I wish it had been a little more stable and successful because it's just a really cool idea. So the idea with a GAN is that you have two networks that you are training together. The loss that they experience is directly related to how not only they perform, but how the other model performs and how they perform together. And they are adversarial. They are in opposition to each other. So we have a generator network and a discriminator network. The generator takes as input random noise or a random seed, and it generates an output image. The discriminator is given a mix of output images generated by the generator and real images from a data set. And its task is to correctly identify whether an input it receives is from the data set or generated by the generator. And notice the generator has no access to the data set. It's just generating based from randomness. All right, so I've adjusted the size so we can see the whole diagram. This diagram is from a source. I will have a link to that source in the notes for this video. I also have a link right in this document that I'm looking at right now. So here you can see we have a generator model, which is kind of like the decoder part of our kind of like the decoder part for our UNet potentially, but you could also try other architectures. The discriminator is kind of a typical CNN. It's performing a classification task. It takes in an image, it classifies that image as real or fake. So this is just an ordinary CNN. It's just that the data is coming in a slightly different way. So the generator, like I said, does not see any of the images from the data set. It's given randomness, some sort of random seed or a random image, and it generates an output image the same size and shape as the data set. The discriminator gets randomly something generated by the generator or a real image, and it says real or fake. If the discriminator is correct, if it correctly identifies real and fake, then it is reinforced, but it isn't given a huge amount of loss. If it is correct about it being a fake, then the generator is updated with a large amount of loss because it lost that round, right? It presented a fake and the discriminator called it fake, so it loses. So then it gets a high loss and it has to learn to produce a better output so that it can fool the discriminator. On the other hand, if the discriminator says that a fake image is real, then the discriminator gets a high loss because it has made a mistake. Or if it says that a real image is fake, the discriminator gets a high loss, and there would be lower loss for the generator when it produces a successful fake. So it's almost like co-evolution, right? The they're not really evolving. That's not a really good really way to talk about this, but they are learning together in competition with each other. So as one improves, it gets an advantage, the other one starts getting high losses, which causes it to change faster, and then when it starts to win, then the first one will get high losses. That's the theory anyway. And they worked pretty well, and they generated images that were recognizable. Now, there were issues with these. I've worked with them a little bit, just a little here and there, and generally speaking, they were extremely difficult to train. There was a lot of tweaking of the models that had to happen, and they had a propensity to just have the learning collapse. So instead of competing with each other and staying more or less, equally good and pushing each other to improve, one of them would just simply fail. The generator would fail. It would just generate garbage, and the discriminator would win every time, and the system would fail. Another thing that I've seen happen is the generator would learn to produce one image that the discriminator could not identify, and it would just keep generating that image as long as the discriminator could not find it, rather than like generating the image based on the random value that it was given. So they were tricky to train. They were finicky and a little fragile. Their learning could easily go awry. And there were certain visible artifacts that were relatively commonly generated. So not everything the generator would produce would look realistic, because the discriminators just never got that good. So it was great architecture. It's a really cool idea. And you never know. Somebody could tweak it and it could come back and be a good competitor. But it isn't really what most AI generative systems that generate images are actually using these days. I say that like this was eons ago. This was like 5 years ago that GANs were still pretty much pretty good. What has taken their place? Well, diffusion networks. In a diffusion network, we have, again, sort of an encoder and decoder happening. There's an encoding phase and there's a decoding phase. But the way that this works is quite different. So the encoder phase, so we start up here with an image, and the encoder phase generates a sequence of images. Each one has had a little bit more random noise added to it. So we start with a pristine image, we add some noise, we add some more noise. We keep doing that until we're pretty sure that for the most part the image is random. We can't really see any of the features in the image remaining in what is there. That's the encoder phase. And typically with a diffusion model, there is no learning that's happening during this phase. It's just a process of adding noise to images. But we keep this sequence of images. We remember it. And we use the sequence as targets, sequential targets, in the actual decoder phase, which is where the learning happens. So how does that work? Well, we start with this image, the rightmost, most noisy one we created, and we train a model to go from this image to the one that came before it in the sequence. So that little model that sits in between this step and the previous step, it doesn't have to produce the pristine image. It just has to go from the noisiest to the second most noisy. And then we have another layer, another set of layers, another model that's doing the next step. So between the second and the third, less noisy, there's another model that's learning to go from this point to that point, from this point right here to that point, and so on. So what the training actually happens by setting intermediate targets for these little machine learning layers or models that are all strung together in a sequence, and the final target is in fact the original image. So this is an encoder-decoder model, and it is doing auto association, because the ultimate final output that we're judging it against when it's training is the original image. Now, once it is trained, we do what I talked about before. We chop it apart. We extract only the decoder portion, because now we can take random noise and feed it into this decoder portion, and it will generate something meaningful and, as it turns out, quite realistic looking at the other end. Now, these models get more complicated because even this model has not been super perfect, and so I'm just going to talk in broad generalities about how these diffusion models work a little more. All right, so I have a couple more diagrams here. These are from a really nice tutorial, and that goes into way more detail about how all this works. For purposes of my course, you don't need to know all this detail. So this is just a teaser of things that you could look for. So the original pure diffusion model, this is like just a more technical way of describing what I talked through in the previous diagram. We start with an original picture, we go through the forward diffusion process, and we generate a series of images that are increasingly more noisy. And we get to the noisiest, which we're calling x sub t. So the sequence of images we're labeling as x0, x1, x2, all the way up to x sub capital T. The learning actually happens in this next section. So we start with x sub t, and it's looking at a U-net that is trying to learn to go from x sub t to x sub t minus 1. So the original, or some at least versions of these, actually used the U-net architecture. It's a little mini encoder-decoder. And in this case, it actually also had some information added that allowed you to indicate which step of the process it was on, which might help it to learn. But you want to think about these U-nets as potentially being, I suppose they could be the same model, but they could be separate models. So this one is tuning itself just to operate in this really noisy environment, whereas the one at this end is taking a small amount of noise and producing a final image. Now, if you look at the x0 that gets produced by the decoder and you compare it to the x0 we started with, they are not identical. But the goal is, the target is to be identical. So as it learns, that's what its goal is. All right, so this was the general diffusion approach, and it worked pretty well. What happened, though, was we had other things that we wanted. We would like to also incorporate text. We'd like to be able to have a text description of an image that we could then integrate along with the x sub t, so that it has this text and that should guide it in what it's supposed to produce. Because that will give us a much more usable system. Somebody can put in a text description of what they want. We can pair that up with random noise and then see what the model actually produces from that. So that was also a goal. That's an additional layer of complexity that we can in fact add. But at the same time, people discovered the Stable Diffusion, which worked better and was much more efficient to train. And that's what I want to talk about next. So I'll just say, one of the downsides of this is that we have not just one U-net to train, but a whole series of them. That's a lot of training. The Stable Diffusion approach leverages this same idea of encoders and decoders to improve things yet again. So let's take a look at, okay, so I'm not going to worry. I have this little yellow part at the bottom of this diagram, which looks really close in at exactly what's going on with some of these pieces, but I'm just going to look at the main outlines of it. So the main innovation that Stable Diffusion added was realizing that we can build encoder-decoders for images. So for an audio associative system, you could start with just a U-net and train it to encode and then decode a particular image. To do auto association, as we've talked about in earlier videos, to do auto association, as we've talked about earlier in this video. So the innovation here was to realize that the adding noise can be done to the compressed representation you get from an encoder instead of to the original image. So the first thing to notice with Stable Diffusion is that there's this extra layer before we get into the diffusion process. We're taking the image, we're running it through an image encoder that has already been trained. It produces this compressed, condensed representation, which they're representing as this cute little matrix with colors in it. It's not an image anymore. It's like a collection of features, right? This is often called a latent representation, or we talk about all of the different possible representations that look like this as being a latent space. It's a space aside from the image, but related to it. We can transform between things in this space, and we can use the decoder to get back to image space, or we can take an image and put it into this latent space. So you'll see a lot of terminology around those terms as you look at image generation and Stable Diffusion. So yeah, we take the original image, we convert it into this multidimensional, potentially matrix, and then we do diffusion on that matrix. So we just add random noise to it through the forward diffusion process, remembering each one of the iterations that happened as we went forward. And then we're going to take that representation, and notice we do have the time, like where we are in the sequence. We're at state ZT, so we're at time T. That information goes into this UNet, but we also add into the UNets what is called conditioning. It took me a while to figure out what people meant by conditioning. I admit I had to dig through some resources. But conditioning basically means other non-image factors that we want to integrate into things here. So that could be other images. Maybe you want to generate images like other images. So you would like to be able to encode them and pass them in here. Text is the big one. But there could be other things as well, other kinds of representations that you want it to pay attention to, semantic meanings, I don't know, whatever it is that you want, you can actually incorporate here. So we have this other encoding process. It's encoding the text, it could be encoding other images, and then that information also goes into this network, along with the randomized encoding and the thing that tells it what time, which step in the sequence it's at. And then this whole bottom section is learning. We present it with examples, and we present it with the text that goes along with them, and we try to train these UNets so that they can make the jump from one step to the previous, from the previous to the one before that, all the way back to this representation, which should be similar to, if not identical to, the one we started with. And then we run that through a decoder to get the final image. It's ingenious. Why is this an improvement? Well, part of it is just that we've found a way that we can easily integrate these other factors that we might want to integrate into our model. And this latent representation, it is much smaller. So there's just less work that has to happen in order to do the diffusion and the training. It makes the training faster. And as it turns out, it makes it more stable too, because this other representation is somehow condensed. It captures the details of the pictures nicely. So this is how Stable Diffusion works. Still very hand-wavy, not going into all the details. You can find some resources in the description of this and just links in my documents as well. All right, so this is just to give you a flavor of how image generation works. And then what I encourage you to do is to go and play around with some of these systems. There are Stable Diffusion systems out there that are open source. You can actually see the code in action. You can also just go and play with existing image generators and see how they do. And what are their positive and negative features? Where do they go right? Where do they go wrong? They're very interesting, And we think a whole lot about them because of their social impacts, which is a whole other issue. But just understanding what they are doing and what they aren't doing is, I hope, really interesting and helpful to you. I'm going to stop there. I will see you all very soon.